Anyhow, we're getting started here, guys. Thanks for coming. Brian is trained as a software engineer and a physical geographer. His PhD research focused on eco-hydrology modeling in urbanized and forested watersheds. This work included tools to support reproducible ingest and transformation of geospatial data, as well as model calibration and uncertainty estimation using HPC research. He has current and prior experience in software engineering, Internet of Things, environmental monitoring, geospatial data storage and analysis, and managing safe, agile teams. His professional interests include developing workflows for reproducible analysis. Dr. Miles is currently focused on translating research codes and algorithms into deployable software artifacts, supported by robust documentation, automated testing, continuous integration and deployment, observability, and fault tolerance, as well as scalability. And he's our very own from CCOM. So thanks for coming, Brian, and the floor is all yours.
Great, thanks, Brandon. So today I'll talk with you about how software engineering, at least from my perspective, can help support at least and hopefully accelerate your research. Before we get started, I just wanted to share some images of playing around with DALL-E 2, one of these AI image generators, and I typed in something like hydrographers writing software. And this is what came back. I hope, well, you can tell me if this is what it feels like. I hope it doesn't feel like this. If it does, I'm sorry. The closer you look, the stranger it is. Yeah. So about me a little bit more, I kind of think career paths are interesting, especially, PhDs. There's lots of different things you can actually do. You don't just have a professor. So I originally started my career being interested in software development, wrote software for a few years and liked doing it, but wanted to solve problems that I was interested in, namely environmental and geospatial problems. Did a master's in natural resources at UVM, working in land use modeling and energy policy. Worked for a few years doing coastal energy, technical outreach support and things like that in North Carolina. Decided I wanted to learn more environmental science. I saw this cool fluid dynamics, environmental science stuff with wind. Did a Ph.D. in geography at UNC, ended up doing the hydrology modeling. Worked for a few years in hydroinformatics as a research scientist at UNC and at University of Louisiana at Lafayette. Did a stint in between doing some work in the private sector and Internet of Things and environmental monitoring. And I joined CCOM about a year ago to help accelerate research through software engineering. So today I want to talk about a few topics in roughly this order of importance. I think but the first one I'll talk about is integrated development environments. I put that first just because I view it as sort of a enabling technology that can make it easier to use these different techniques, apply these techniques and tools. Well, let's talk about version control, automated testing, code quality tools, dependency management and software packaging, software security, continuous integration, and also touch a little bit on open source licenses. Just curious, show of hands, how many people are using or have used a version control? This is an important one. Okay, that's good. That's good. First, I just wanted to cover a few overarching principles of why adopting, or I think adopting software engineering practices can help your research. And a lot of these principles will kind of weave in and out of the different things we'll talk about. So the first would be protection, and to protect and preserve your the software that you're writing for the center and its sponsors who pay for it. Another consideration is to help your invention story, support that, give you the background information in case you need to license or patent. Ideally, software engineering tools can help with collaboration and code sharing, which hopefully will accelerate research. One that's really important for me that I'm very interested in is to help ensure that your analyses and your algorithms are robust and reproducible. And I think there's some tools that can help with that. And also, things like just help you with oopses, accidentally erasing things, doing the wrong thing, getting back to something that was known to work. These are just some tools in here that can help with that. So let's dive right in. Although actually, before we dive in, I just want to say, if you do have a burning question, like a clarifying question, please ask, but I want to keep the discussion towards the end, if possible, mostly so we can make sure we just get through it all. So integrated development environments, what are they? I think of them as software packages that integrate code editing and quality analysis tools, debugging, version control, testing, all sorts of things these days. Basically, it's a toolkit to help you be more productive and help you steer you in the right direction in terms of software practices. There's a few examples here in no particular order. Spider is a popular one. Python has been in the past. Eclipse, which started in the Java world, also now is do C++ development, Python development, other things. VS Code, Visual Studio Code, it's a Microsoft open source product. It's not to be confused with Visual Studio, which is their Windows development environment. It's very popular on the web and supports lots of different toolkits. Another one that I like to use is PyCharm. It's a Python environment. They have a free and a non-free version. It's by this company JetBrains that makes really robust tools across a different set of languages. So these are some that you may know about. Why use them? Well, I think they can help you to navigate and understand your code. This is an example of me just taking a function that I wrote and saying, well, show me where it's been used. You can kind of, figure out, how your different pieces of code relate together in this way and come to understand or re-understand your code. IDEs, integrated development environments, can make things like writing tests, using version control easier. They kind of have some tools in there, so you don't necessarily have to dive in and use command line tools if you don't want to. Can make debugging easier. Visual debuggers have saved me a lot of time, I can say, making it easier to step through code, set breakpoints, examine many variables at a time. And that's something that a lot of development environments provide. These environments also help generate documentation automatically for you sometimes, but at least stub it out for you so you can fill in the details, but you don't have to do the laborious typing. They can also generate some code for you. This is more applicable in things like C++ or Java, like a strongly typed language, where it can just avoid you having to type a lot of boilerplate. Also, these tools help with things like automated refactoring. So if you need to restructure your code, even simple as renaming things, it can kind of trace through where a variable or a name is used and rename it for you. It can do more sophisticated. Some of them could do more sophisticated code restructuring as well. Okay. So next, I'm going to kind of cover these fairly shallowly, but hopefully get through them all. So version control. What is that? So it's kind of what it says on the tin. Software tools that track the contents of files, usually text files, and allows for easy differencing between current and past versions, allows you to merge your work with collaborators, allows you to restore previous versions. Some examples of version control technologies, going back in times, RCS and CVS, probably don't see those very much anymore. SVN is another somewhat older one. It's a little bit more modern, still in use. And then the more modern ones are Mercurial and Git. Git was developed by Linus Torvalds, the person who wrote the Linux operating system kernel. So it's based in a lot of experience with collaborative development. And these recent version control systems like Mercurial or Git are distributed version control systems. There's no central repository. By convention, we'll often refer to one as sort of like a central repository. So if you haven't learned any of the older ones, it's actually probably better just to learn the newer ones like Git, because you'll unlearn as much. But distributed version control makes it really easy to share code using these platforms like GitHub, GitLab, Bitbucket, etc. And these platforms have really powerful tools for analyzing code and managing a collaborative software development. So this screenshot on this slide here shows an example of that for a project that I'm working on, the bathymetric attributed grid library code. So this is a screenshot from part of it's called a pull request. So I have one branch of code that I'm trying to, with new features, I'm trying to merge into the main line. And this pull request tracks, some of the details of the changes. You can see change the version number, that kind of thing. Whoops. And we have our first technology issue here. So I have a little commit message here. It says what I did for a particular change. And then there's a plot that did a test on the code, showed me some results, and then we can track our conversation about how we're collaborating. So these are really powerful tools that are pretty easy to use. So why use it? Protect and preserve your code for the center and sponsors. As stated before, give you a clean history when you need to declare an invention to the university, which is a requirement of our funding. Hopefully accelerate efforts through code sharing, protect against these accidents, these oopses. And then I think more and more to integrate with other tools through things like continuous integration. And then we'll talk more about that in a little bit. Integration. I think version control also can help you, at the very least, help you remember what you did and when, and at best helps you remember why you did things. Because every time you check in code, you have to write a little message, and if you write good messages, you're leaving breadcrumbs for your future self, so you can remember what was going on in your brain. And I think also version control, because it's creating these individual sort of cryptographically stamped versions of your project, can help you prove to yourself and to others that a particular version of your code or your algorithm gives a particular set of results. And this is especially true when combined with automated testing, which we'll talk about. This graphic here is a link to it there. The original source shows the Git flow branching model. Is a very popular model that kind of came together probably about 10 years ago or so. Just showing how you can use a distributed version control system like Git to manage complex development of code in one branch with your released code over here, and new feature developments being merged in, and bug fixes, things like that. So you can see that this will facilitate fairly complex development and collaboration workflows. So automated testing, what is it? Again, it's kind of what it says. Code that exercises some or all of your system, often written using testing frameworks that can help run your tests and also report results back out. The key point here, I think, is to spend less time testing your code yourself, sort of running it and kind of eyeballing it, saying, yeah, it looks about right. And to spend more time writing test code. You can still test it, eyeball, get that intuitive sense if it makes sense. But the more you write test code, I think the better you'll be, better off you'll be long term. There's a few different kinds of tests you can write. This may not be all of them. There's unit tests, functional tests, and I think integration tests most broadly. So unit tests are testing of a very discrete unit, like a single function. So like this example here, was working with Brian Calder to port some MATLAB code for the crowdsourced bathymetry project, port that from MATLAB to Python, and Python, the libraries I'm using don't really have a curve fitting function that looks like or behaves like the MATLAB curve fitting function. So I wrote my own that kind of mimicked it, and I wanted to test it, right? So I just set up a little test here, test fit, some test data, I run the function, and then I make some assertions. And if those assertions fail, the test framework will tell me. So I'll know if I broke my code accidentally. Functional tests kind of take this to the next level where you maybe start to put together a few units and see if they integrate. End-to-end testing would be sort of taking an entire system and running the actual system end-to-end to make sure it works. Why do it? Well, automated tests can be run over and over again. And it might take a bit longer to run or to write these tests than to just test by yourself. But when you write these tests, then you can kind of amortize that cost. So the cost of invested in, the time invested in building the test will sort of pay for itself over time, hopefully. And then once you have automated tests, you can do things like use code coverage tools. I'll tell you what percentage of your code is covered by a test. And with good code coverage, it's much easier to prove to yourself and to others that your algorithm or your analysis does what you think it does. And then code coverage, you can kind of start off small, but then as your investment in your code grows and you say, oh, this is something I really care about and want to keep, you can build your coverage up. And then ideally, when it comes time to publish, you have a really high degree of coverage on your code, and it gives you more confidence in your results. And this can help with the reproducibility of your work and help convince others that they want to try to use your code in production environments. And this screenshot is just showing me running a test suite in my IDE. So I had 22 tests in this test suite, and they all succeeded. Hooray! It doesn't always happen that way. But also the nice thing about this IDE in particular, PyCharm, when you write a test, it recognizes it and it puts these little green triangles next to them, and you can just click on them and run them usually, which makes it super easy to just run stuff quickly. Okay, so related sort of to automated tests or getting into code quality tools. This is also something that we'll kind of want to run in an automated environment, but these are code analysis tools to identify possible programming errors or bugs, including security errors, which we'll talk about next. They can also identify stylistic formatting choices that make it more error prone, so harder to understand your code. They can identify missing documentation or documentation that's inconsistent. These tools can be used, in a standalone fashion, like in a program you run on the command line, or as part of a continuous integration environment, or you can actually, a lot of the IDEs have these things built in, and we'll show a little example of that in a minute. Why do this? Why use code quality tools, also known as linting tools? Well, they catch errors in your code through static analysis, so they don't actually try to run your code. They analytically go through paths that are possible in your code and identify potential problems. And this is especially important in dynamic languages like Python. It's not a statically typed language. It's much harder to prove sort of analytically that something works in Python. There's no type system. So there's dynamic, there's static analysis can help with that. And also, we want to ensure that our code is well written and well documented. That's part of preserving it and maintaining our investment in it. Something that is well written, it's easier for others to pick up and use, and it's easier to maintain in the future. It's not a liability as much. So here's an example from we have a continuous integration environment here at CCOM, where when we make changes to the code, it automatically checks it out. I dug into one detailed error that we found. It identified this is a development branch, so it's not supposed to work, but it found on line 36 of this particular file an undefined variable, which in Python will cause your program to not work. So we know that ahead of time. We don't have to run it. While we're talking about code quality, I wanted to talk a little bit about documentation, a little bit more philosophically, maybe. Obviously, please document your code, ideally with inline comments. Remember, you're writing this for yourself as well as others, your future self. What you want to focus on, though, is to document the intent, sort of the what and the why of what you're doing, not the how, not the nitty-gritty steps. So this kind of frees you a little bit. You don't have to worry about every little line explaining everything. Adding one to the variable, and if your code is written well and in the idiomatic style of the language that you're writing in, you shouldn't really have to be going into the how all the time. People should understand it. And there are times when you might want to do that, though. If you're doing something strange, like for numeric performance or other reasons, you might have to go into the details of saying, I'm doing something really weird. I'm going to tell you what it is. And also in languages like Python, get into the habit of documenting your code with type hints. So Python, you don't have to declare variables as types or anything, like an integer or a string. but you can optionally give it a type handle. And doing this makes it much easier for static analysis tools to find errors. It can make it easier for you yourself to understand it. So you can kind of see in this screenshot, there's a little dummy function I made that has some type hints. You basically just put the type after the variable colon type. And so we have an input 1 is a string, input 2 is an int, and 3 is supposed to be a float. These get thrown away at runtime. The interpreter doesn't care what anything is, it just runs it. But it allows tools like this in the IGE to catch, it says, it can catch errors basically if you're using this incorrectly. You can catch it. In this case, this error that it's showing is actually a little bit unrelated. It's just saying, hey, your documentation's out of sync with your function. So I haven't added input 3 to the documentation yet. But if you were using my function somewhere and you passed it 2 integers, a string and 2 integers, it would flag it. So, hey, this doesn't look right. So now I want to talk about dependency management and software packaging. This is like one of those, especially if you're doing research, writing research code, it's like this annoying thing that you don't want to have to worry about, but is important actually, I think. It doesn't feel like it's adding value, but I think it does. So dependency management tools are tools that help you manage the installation of the libraries that you need to run your code. You're probably not writing all the code that you need. You're relying on packages that other people wrote. If it's Python, you're probably using NumPy or Pandas or something. There's innumerable libraries out there for you to use. So you probably want to use dependency management to sort of affirmatively declare, here's what this software needs to run. Related to that is software packaging. You can actually package up your code to make sure that it's really easy to install. And then relatedly, you can use tools. Some of these dependency management tools have this built in, the ability to have an isolated development environment, so you can install dependencies independently of other things on your system. And so the reasons why we do all these things is to make it easier to install the correct versions of dependencies needed to run your code, so that it behaves as expected, or maybe it won't even work at all. Avoid conflicts, like I said, between other incompatible versions, make it easier for others to install your code, and then also to make it easier to do automated testing. Because if your code has dependencies, if you're going to do automated testing in a continuous integration environment, you have to declare those dependencies, otherwise the environment won't be able to install your code usually, or run the tests. Wanted to give another philosophical side note on dependencies or libraries, other code that you try to pull in to do your work. Every line of code you write is a liability because you have to maintain it, but every dependency you link to your code is also a liability because you have to rely on a third party. Now your fate is tied to someone else's, which is always the case. We're always interdependent, but the trick is to balance these two things, right? And there's this cautionary tale I linked to here, how one programmer broke the internet by deleting a tiny piece of code. Probably remember, some may remember in 2016, I don't know. Yeah, the left pad debacle. So in the JavaScript world, people started relying on all these hundreds of packages to build their web applications. Someone wrote one called left pad because earlier versions of JavaScript were very limited in what they could do in terms of string processing. They needed to pad a string out to make sure it was a certain number of characters wide. So they wrote this library and published it. And then several large JavaScript frameworks that some important websites are built on decided to use this framework or this left pad function. But then there was a dispute. The author of this function unpublished it because he got angry about some other things. And all of a sudden, people couldn't build new versions of their websites. It's a fairly easy problem to solve, but in the moment, people were panicking. So just it has happened and can happen and will happen. Problems with dependencies. And another problem with dependencies is security as well. And I'll talk about that software supply chain, but I just wanted to touch briefly on a few security concepts. One being the build chain. And so that idea is the build chain is the software tools that you use, like your IDE, your compiler, your build tools, to build and to test your software. The build chain is one source of vulnerabilities. libraries. If you use a compiler that's compromised, all bets are off. It can do whatever it wants to your code and inject whatever it wants, and you may not even do it. Relatedly, a software supply chain. That's the languages and runtimes, the dependencies, libraries that you use when you run your software. Increasingly, that's a source of a sort of attack vector where a malicious actor will take a popular software library out there and create a new version with similar name, similar sounding name. And then some people will unwittingly install that, and it'll do what it says it does, but it may also do some malicious things. And to deal with these build chain and supply chain issues, there's an increasing movement to require software bill of materials, SBOM. This is something that's come out over the last year or so. And this is basically a detailed machine readable listing of all the third-party software that's in your software. Right? And if you're using a dependency management tool, though, I think creating these software bills of material should be pretty easy to do. I have some links in the next slide. Talk about that a little bit. Another thing to know about is automated security scanning. More and more people are doing this. So this is another reason to use these continuous integration environments, which I'll talk about. So basically, they just allow for dependencies to be scanned automatically and to warn you, hey, this library that you're using has a vulnerability. You need to upgrade to this version. These security scanning tools can also do static analysis, like the code quality tools, and identify vulnerabilities in your code. It can show you, oh, look, you have a buffer overflow. This is just an example from Wikipedia of a buffer overflow. You have a buffer overflow in this line, fix it. They also can do active scanning for network systems. So if you're doing something like on autonomous vehicles or something that's networked, that's controlling things in the real world, you can do what's called penetration or pen testing. So it'll actually go out and actively try to break into your system and show you that where you might be vulnerable there. Some security scanning tools out there. There's lots of them. I don't even know all of them. I can't even know all of them. GitHub actually has recently added some, which is helpful if you're using that. The Dependabot alerts that will scan your dependencies, code scanning alerts. I'll look for, like I said, things like buffer overflow. There's other ones I'm familiar with. White Source, which is now called Mint, I guess, scans your dependencies. Veracode. There's lots of other ones. So why do we want to code securely? Well, it reduces chances of ransomware. You might have heard of ransomware attacks. The pipeline, the Colonial Pipeline shutdown that happened last year. Apparently, we were like 3 more days from having serious problems because the fuel pipeline on the East Coast was shut down. That was a ransomware attack, and they just paid it. So basically, a ransomware attack is someone finds an exploit in your system, they break in, they encrypt your data. In this case, it was just billing data. The operations of the pipeline were fine. It's just they couldn't bill people. And they say, if you want to unencrypt your data, give us $1 million. So we want to avoid that. We want to avoid IP theft. Both your source code could be exfiltrated if you have an exploit, or the data that you're generating with your code. So this should be of particular interest for hydrographic data, depending on who you're generating the data for. Also, you could have surreptitious introduction of errors into your data or into your process. Is anybody familiar with Stuxnet? So that was an attack that I'm pretty sure it was the US government, maybe not. Someone carried out against the Iranian refiners, uranium refineries, the centrifuges. So they just took a thumb drive and dropped it in the parking lot, and somebody picked it up and they plugged it into a computer, and it got in, and they got into the control systems for the centrifuges and caused them to break and set back their refining for a while. So this kind of thing happens. So what are some easy things you can do? The rest of this was, the other topics I talk about are just kind of awareness. There's actually some things you can actually do here. I just want to talk briefly about for security. You can enable multi-factor authentication everywhere you can, especially for things like GitHub and Bitbucket. And I know that's annoying, but it's kind of the world we live in. Similarly, we can use SSH keys for authentication for Bitbucket and GitHub. Don't use passwords, and I think you actually can't use passwords on Bitbucket now. So yeah, if you need help with this, we can help make that easier. It's a little harder on Windows sometimes. Don't copy and paste and run scripts. Stack Overflow. Don't use software development environments from untrusted sources. That's part of your build chain, securing that. Don't install software in general from untrusted sources. And when you do install software, try to please verify cryptographic signatures. Sometimes you'll see instructions for doing that. It's actually not that hard once you do it once. Can help. For programming languages, try to use memory safe languages when you have a choice. For applications, that's things like Python, Ruby, Go, Java, Scala, C#, but basically modern languages. For systems programming, that's things like Rust, C++ 11 or later, Swift, Carbon, things like that. And stay tuned for emerging efforts in areas like automated testing and software bill of materials. I put a couple of links in the resources there. First is DoD, second is Department of Commerce, where a lot of these software bill of materials initiatives are coming out of. This is a kind of an emerging thing. So kind of getting to the home stretch, I want to talk about continuous integration and deployment. Again, this is sort of you can think of this as an enabling technology, kind of like IDEs, but out in the cloud for doing stuff with your code. So these are automated software environments that periodically check out your software from version control and build it, test it, deploy it even. You can even have things published from, automatically from a continuous integration deployment pipeline. They can do these tests like we said, unit tests, functional tests, code coverage tests, code quality tests, security vulnerability, and also benchmarking. So if you have something that's performance critical, some open source projects have a rule. You can't check in code that makes our performance test suite go slower. So these are all things that can be automated. Some examples of continuous integration. Jenkins is a popular one. It's maybe a little long in the tooth now, but it's still widely used. We have an instance here at CCOM. If that's something you're interested in, maybe we can talk. There's software as a service, CI/CD tools, Travis CI, AppMayor. GitHub has GitHub Actions built in now. So if you just want to have everything through GitHub, you can do that. GitLab also is another option here. This kind of shows an example of the CI/CD pipeline happening there where code is checked in, the pipeline checks it out, builds it, does tests, potentially deploys it. So why do we do it? Well, we make sure our automated tests are actually run when needed, when code is committed, during code review, merge code. Make sure, really the goal is to make sure obviously bad code doesn't make it into our operating environments. And potentially you can automate software releases and automate other things with it as well if you want. Okay, getting into the end, open source software licenses. What are they? Why should you care? These are legal terms dictating what people can and can't do with a particular piece of software. There's a lot of examples. I don't even know all of them. Listed a few here: BSD license, GNU general public license, GPL, LGPL. You might have heard of. MIT as a popular one. And you should care about these because some licenses are permissive and allow commercialization, but some are not. They're more restrictive, dictating what can be done with not just their code, but with code that you link to their code. So for example, the GNU GPL is kind of pejoratively considered to be viral. So if you link code to GPL code, you have to release your code as GPL as well. So some people don't like GPL for that reason. That's why we have more permissive licenses like LGPL, MIT, and other ones. So you do need to give some thought to the license that's used by a dependency before you use it. You can't just, even if it works perfect, like if it's the wrong license for what you're doing, and you have a commercial partner or industrial partner or sponsor who has certain licensing restrictions, you just won't be able to use it. And then also, ultimately you want to choose for your code the license that best supports the goals of you and your sponsor for what you want with the software. There's some resources at the site opensource.org. They have sort of plain English, non-legalese descriptions of a lot of these licenses. So, you don't have to memorize any of this, it's just good to know about, that it's something you should consider. So I do want to have time for questions or discussion. Just wanted to wrap up briefly and just sort of give a rundown that, we talked today about integrated development environments, which are, like I said, an enabling technology for applying software engineering tools and practices. Version control to protect, preserve your code. Automated testing to prove to yourself and others that your code does what you think it does. Code quality to ensure that your code is well written and well documented. Dependency management to make it easier for you and others to install your code. Software security to reduce the chances of being victim of ransomware or something like that. Continuous integration for making sure bad code doesn't make it into operating environments. And then lastly, open source licenses to protect your rights to determine how your software is used. So with that, just leave it open for any questions or discussion. Don't be shy in general. Please reach out, email Teams or stop by my office. I'm in Chase 248 and happy to chat anytime to see how I can help. Thanks.
So we'll open it up for questions if anyone has any. I got
two kind of unrelated ones.
Okay.
Start with from licensing, from your perspective, what have you seen commonly adopted here at a research center in terms of balancing, there's often a big push for open source software. Then there's, an interest from the university and to protect IP. What kind of license do you typically see? I know my instinct is often to just do MIT.
Yep.
Because it's super permissive. But
Yeah, that's kind of my instinct too. And I won't speak for all the code that's has been or will be developed at CCOM. I haven't seen, I've only seen a small part of it. But my instinct also is to, if there's a lawyer around, ask them. I've had to do this with the state of Louisiana. And at first they didn't really know what I was talking about. So you may have to do some education, but basically we were working under contract for the state. And I was like, well, I'm not an agent of the state. I can't decide how to license somebody. So, do your homework and have some ideas and understand the constraints of whoever the sponsor is. Sometimes they won't have an opinion, and then you can do something with MIT and go with it.
okay. The second question is, you definitely have me sold on IDEs. I use one typically, but in researching, I'll often come across kind of a vocal minority that advocate Emacs and VIMs and all that stuff. Is that a bygone era, do you think, or?
I don't know. I mean, some people do pretty well with Vim. I like to use Emacs just as a text editor. I always say when I retire, I'll learn Emacs, because I don't have time to get
It just seems
to learn Emacs
so much
lists.
harder than
Yeah,
go online.
you can customize anything theoretically, but I tend not to spend a lot of time on my tooling, so I pick stuff does most of what I want. But yeah, I'm not going to fault people if they can get work done with the other things, but I've also worked with people who just use Vim, and then I do a refactor. I'm like, they're like, how did you do that? You changed, 200 files. I'm like, I just use my IDE.
Can we go back to the previous slide? So for a lot of these things here, is there any IDE that you'd recommend that can kind of manage the vast majority? I know PyCharm, they have a sort of version control thing they throw in there. I don't know if they have any automatic testing. But from your experience, is there any good IDE that can handle a lot of these? You don't have to then go and code your own automated testing protocols, for example.
Yeah, you'll still have to write the tests, but once you have them, the IDE can discover them if they're built using like a known or recognized environment framework. PyCharm is good for that. I like it for that. I know the version control stuff sometimes confuses me. In PyCharm, I tend to use the command line if I can get away with it. sometimes it's easier in the IDE. Visual Studio Code maybe is a little better on the version control side. It's been a little while since I've used it. I mean, none of these things do everything, but I know PyCharm, like, it'll do code coverage for you too. Just as a starting point. You know, once you have tests, you can say run it with coverage, and it usually works. Gives you at least something. You probably have to do some configuration, but and the static analysis is pretty good in it, getting better. There's plugins you can integrate with. A lot of that's the thing with IDEs though, is a lot of the plugins, so it doesn't do what you want out of the box. There's often something you can do without, like I said, spending too much time on your tooling to get something better that more suits your needs. Yeah.
Quick question about licensing. Do you happen to know off the top of your head the differences between BSD and MIT just for like practical?
I do not know. I would look at the opensource.org site. It's, yeah. And I know there's like 4 different BSD ones, like 0 clause, 1, 2, and 3 clause. So I don't, yeah.
To keep going on licensing. Maybe you can help me understand. Do I need to copyright my code as well? Or does the license cover my copyright? Because I've often, I worked a lot with Giuseppe, and everything Giuseppe has, there's a license, and then there's a copyright notice at the bottom as well.
Yeah, I think you want to do both.
What does the copyright give you?
I think it's like a provenance thing, sort of like you're saying this
Because it
came
says the
from me.
university owns the code.
Yeah,
the license
yeah. The license doesn't assert ownership. It just says what other people can do with it. I think the copyright asserts the ownership. Obviously, that could be disputed, but stuff that truly originates from you is pretty easy to show.
No, I think, yeah, because I think the university owns everything I do at this point.
Yeah.
Which is okay.
You know. Yeah, in the back.
I just comment on the licensing. I know that the NOAA grant with OCS, they're pushing specific types of licenses.
Okay.
Brian knows about that. I don't remember exactly what all that is, but Brian can answer that question. And I'm pretty sure that all the grant agencies now are kind of pushing towards specific licenses. There's a whole federal office pushing to open source for federally funded things. I mean, of course, if it's like in Department of Defense secret thing, I'm not gonna have you pushing it publicly and putting it publicly on the internet, right? But there's a whole federal office and kind of outlining the advantages and what kind of licensing they'd like to be seen used and all that stuff. So
Yeah, that's a good point. I think the maturity of the agency is changing. It's good in this area. 5 years ago or so, 10 years ago, definitely they had no idea. So you'd ask them, and either black hole, nothing would happen, or they'd say do whatever you want. I think, but now it's great that they have opinions, because then you can just do that. You don't have to worry. But just be aware that there's probably a preferred license depending on your sponsor.
Yeah, it's a very interesting balance because there's no on the one end for CCOM, and there's the university.
Yep. And you can apply multiple licenses to things too. So if people do that, I don't know exactly how that works, but it's an option. Anything else?
Do the CI stuff we have here at CCOM,
Yes.
do they integrate like with GitHub kind of seamlessly or something?
I wouldn't say seamlessly. It integrates with, right now we have it integrating with Bitbucket, commercial Bitbucket. We have to do a little work because it's in our DMZ, so it's firewalled off. So yeah, it's a little bit of work needs to be done, but we can do that. We can scale it up. Right now it's not, it's not built for hosting dozens or hundreds of projects, but we can scale it out as needed. Did anybody think they're gonna do any of these things? people?
It's a version.
Some people don't know it, but they will.
So is there anything within CCOM that being kind of pushed by IT for like group collaboration and version control in like a research lab, or if you're doing things across the group? Or saving it so it doesn't die? Is there, you've got a lot of tools here and you can go about that in different ways. You don't have to push it all to the cloud and GitHub, but
We do, I mean, I don't know the official word or policy, but I know that we have a Bitbucket account that we use. And I know I personally use that. You can make private repositories, so you don't have to feel self-conscious. I have private repositories. I'll even just put notes there. I don't know if you're familiar with Markdown. The formatting tool, super easy to write in and produce nice looking output. I have notes on things that I just put, Markdown notes I just pushed to a repository. But so yeah, Bitbucket is one. I know people use GitHub for some projects too. That's
Sounds got a
totally permissible as well.
We distribute EPUB through GitHub.
Okay. Yeah. So I think those are two of the major ones. And I would encourage their use. Probably GitHub is more mature and used more widely. It has more bells and whistles. It's nicer. But if anybody, I don't know, like as an action going forward, if any of these are particularly of interest, I could put together something on one of these. We could go in deep and have some more practical nuts and bolts stuff too. So, if you have an idea for something like that, please reach out.